Hello, welcome. This is question 1 for the AQA A2 Unit 4. Okay, this is section B, the written paper. Okay, which the videos hopefully won't be as long as it was for the multiple choice, because I'd have to go through every potential answer someone could have put. Alright, okay, so this diagram is for later on in the paper, but I've just gone ahead and thought, I'll draw it anyway, so I have to pause the video, walk over, so you physically walk to the camera, press a button, draw it, and then start it again. So I just thought I'd put that in there. Can't bother. So this object on the left, this system on the left. Now, we're not asked to do anything with it. There's nothing. Sorry. Oh. Damn hay fever. If only I could be bothered closing my window. Okay, so anyway, we're given that this system, where there's a spring and there's a mass suspended. Obviously, it's going to oscillate simple harmonic motion, that's obvious. But we're not asked to do anything with it in terms of we're not asked to calculate anything. All we're asked to do is define a few terms for 1A. We're asked to define what force, vibrations and resonance means. Okay. So, it's worth 4 marks. Obviously, there's two points you need to mention in each definition. In other words, 2 points you need to mention for when you're defining force vibrations, and 2 marks for defining when you're talking about resonance. I can't even speak anymore, God's sake. Anyway, okay, so force vibrations. Now, the most common thing, and I think the thing that should come to your mind, I think it's the only thing I wrote for force vibrations anyway, initially, is that they're vibrations which occur because of an applied periodic force. So vibrations which occur because of an applied periodic force. Now, that's just a fancy way of saying the fact that you apply a force at the same point in the cycle. Okay, so as soon as it comes to you, you push it away. If you're thinking of a spring, okay, and you keep pushing it at the same point with the same force. Okay, that's pretty much what it means. An applied periodic force. Okay, but I'm sure there's other ways to word that. But that's only 1 point. Okay, so the second point you need to mention for force vibrations is it's a repeat, because we need to first of all relate to what force vibrations is, and then just for the extra mark, okay, you need to mention that it goes up and down. Now, that is weird, but that's one of the things accepted, okay? So it's with a repeated upwards and downwards motion. Now, would I have thought of that in the exam? Probably not. Do I care? No. Because now you know that question probably won't be asked in this exam. It probably will do, because I've said that. So that's force vibrations. I'll just put FV again because I'm lazy. Now this next bit is resonance. Now, again, the first point I would have expected everyone to put, okay, or obviously for those of you that had a fair idea of what to put. Okay, now you should know that that it's kind of related to force vibrations, okay, because that's kind of an applied frequency almost, if that makes some kind of sense. But if we displaced this mass and we pulled it down and we let it go, and it would vibrate in an upwards downwards motion for a period of time until it stopped, obviously, but that frequency it was vibrating at, when you simply just displace it and let it go, okay, that is the natural frequency. And the thing to state with whatever it's asking about resonance is that it occurs when the natural frequency is equal to this applied frequency, which you could say is to do with force vibrations. Now, applied frequency and force vibrations are very similar, as you can kind of tell. Now, what else would you put for resonance? Because that appears to be everything. But as we know, this is 4 marks, so you need to put two points for each mark. Sorry, 2 points in each definition, okay, to get the 4 marks. Well, when whenever you see something in resonance, the amplitude is always the biggest. If the natural frequency is bigger, if the natural frequency is bigger than the applied frequency, you can still increase the applied frequency. However, once the applied frequency becomes bigger than the natural frequency, it will break the system, okay? Because it will be going faster than it naturally would want to, okay? So therefore something's likely to break, okay? So therefore it's just something, again, you probably should just have in your mind that this means that this results in the largest energy. It says in the mark scheme, this results in the largest energy change, and obviously that comes from, it's the largest amplitude, so therefore there's the largest difference between the biggest speed at the bottom at the equilibrium position and the biggest potential at the highest point, okay, at the point of maximum displacement, okay. So you could just say this results in the largest energy change, or this results in the largest amplitude. Largest amplitude for the system. I just put largest amplitude again because I'm lazy and because I can do whatever I want. Okay, so that's force, vibrations, and resonances. Now that's 4 marks. That's half the marks of the question already there. Okay, and to be honest, I could quite easily, even if you knew what you were talking about, it's quite easy to get 2 marks in that question. Okay, so there, obviously, a quarter of the marks have gone. I'm good at math. I really am good at math. I can do quarters and everything. Okay, so anyway, apart from the fact that I'll probably get shot, let's move on. Okay, so now we have to move on to this excellent drawing I've drawn here. So we've got this thin thread, okay, which is suspending this light paper cone, and in red, what I've drawn is this metal ring, okay, and these arrows are just saying it oscillates, it's kind of like a pendulum kind of thing. Okay, we're told that the bob is displaced so that it oscillates in a vertical plane, as these arrows kind of show. The oscillations are subject to damping. Are the oscillations of the pendulum more heavily damped when the cone oscillates? So basically this question is saying, what is the effect of this metal ring on the damping? Okay. In other words, does it increase the damping? So does having an increased mass of this metal ring increase the damping? So does it increase it? Well, actually, this question, the question is stupidly worded, I think. It's saying, when is the system more heavily damped? Is it when the metal ring is on the paper cone, when it is not, or it has no effect? It doesn't matter. Okay? And the box you would tick is cone oscillates without ring B. Okay? Well, it's actually B, it's just cone oscillates without ring. And that is because the damping is actually caused by this mass. Now, if it was in a mass spring system, then I think that is where it occurs. But when it's in a pendulum, this kind of thing, okay, the damping is only affected by the air resistance, because it's not going to be, because this mass, yes, it would want to pull it down more, but we assume this thread doesn't change in length, okay, so therefore it's still going to experience the same. The only thing that's going to change, okay, when it's going left and right, is the mass. But as that doesn't affect anything, okay, all that's gonna happen, okay, is that because the damping is only caused by air resistance, the area is the same with or without this metal ring. We assume the metal ring is so small, okay, that it doesn't actually affect the area, okay. Also, a small proportion of energy is removed on each cycle, hence more heavily damped, okay? Because remember, heavy damping means it's going to take longer to stop, okay? Because it's too much force, that's the way I worded it, okay? So it's going to keep going for a greater period of time, okay? So the three things I mentioned, okay, is that the damping is only caused by air resistance. Now, if this was a mass spring system, I'd say it would be different, but you have to apply it to whatever you're looking at. Fortunately, you can't apply it to something that you just make the question. Cross out I've always thought about cross out a question, coming up with your own question, answering it A star, easy. Anyway, so air resistance is the only thing that causes damping. So where this causes damping. Again, you can answer this in bullet points, or like a 5-year-old, like I'm doing. Stupid. And the air resistance causes damping, and then you need to explain the fact that the metal ring doesn't actually have any effect on the area. Okay. Okay, and you also need to state that the smaller portion of energy is removed on each cycle, hence more heavily damped when there is no metal ring attached. Okay, because when the metal ring is attached, there is more energy taken away because it has to put in energy to move this metal ring, okay? And when it's not there, it doesn't remove as much energy, okay? Because obviously some of the energy is put into moving this metal ring about, okay? But when the metal ring isn't there, it's going to be taking a smaller percentage of this energy away, okay? So therefore it takes longer to stop, hence more heavily damped. That's what it was trying to get at there, okay? So we just talked about the fact that the small proportion of energy taken away on each cycle. Okay, so that's your answer to B part 2. Remember, B part 1 was just explaining, was just ticking the box that said the cone oscillates without the metal ring, and hopefully I've kind of explained it there. But as I say, there were loads more answers online, but see, just my internet hasn't been the best, so good hope for uploading this video and the 3-hour section A to it. Okay, so thanks for watching, and we'll see you in the next video.